So we are going to talk about radial motion. A quiz, not test. Quiz. Angular velocity. Remember what angular velocity is? Okay, yeah, that was one way to describe it, I suppose. It is described as an angle, that's theta, divided by time. Now the angle is in radians. Time can be in any unit. Generally, it is in seconds. Symbol for angular velocity is that kind of script W. It's called omega. So, some things that we need to know about, all right, excuse me. One cycle. Cycle, there we go. Equals one complete revolution. Which equals 2 pi radians. So 1 revolution per second, 1 RPS, equals 2 pi radians per second. So there are some conversions we're going to be doing with these. First of all, our frequency. If omega is equal to that angle, or let's just do that angle over time. Our frequency the frequency, remember, is the number of cycles per second. Correct? Make sense? Okay. So frequency is cycles per second. That would be revolutions per second. 1 revolution is 2 pi radians. I feel like I'm babbling a little bit, so I'm going to get to the point. So the omega is your frequency times 2 pi. Because remember, your frequency is the number of revolutions per second. Each revolution is 2 pi. Usually written as omega equals 2 pi f. And the units do work out because omega is in radians per second. Frequency is in hertz, usually, which is per second. And your 2 pi is in radians. So some other units that come from that, if I want to find the frequency, and I know the angular velocity, all I'm doing is solving this equation here. How would I solve that for f? Divide by 2 pi. So f would be equal to omega divided by 2 pi. Or omega, of course, is just cycles per second. Or we'll leave it at that. The other one gets So if I give you that a system has an angular velocity of 40 pi radians per second, what's the frequency? Yeah, frequency is omega over 2 pi. So 40 pi over 2 pi. Pi's cancel out, 40 over 2 is 20. That's just 20 hertz or 20 cycles per second. 20 per second is a frequency. You have frequencies listed on your, for your cell signals and stuff like that. Remember what they were? Was it 800 or 80? 800? And 80 megahertz is a radio frequency, isn't it? So 800 megahertz would be 800 million hertz. What is the angular velocity of the transmitter? 800? What's the angular velocity of the transmitter there? It's 2 times pi times f. So 2 times pi times 800 million. It is 1,600,000,000 times pi. You could leave it like that, or 3.14 times 1.6 billion. So 5,024,000,000. Got 2 more zeros to put on there. 1.6 billion pi, not 1. That's radians per second. That's a pretty healthy angular velocity. Why is this important to you guys? How is AC current generated? Anybody know? There's 2 ways of doing it. You can either have huge coil of wires and a big magnet, and the coil of wires spins in the magnet, or you can have the coils of wires and the big magnet spins in the coil of wires. Typically, it's the coils that spin. So what you have is you have the coil of wires. Of course, it starts at one point that leads out, coils around, and then it finishes at another point. That's another lead out of that coil. And it goes to contact, so it can spin freely. Generally, there's a shaft, and on that shaft there is this wire comes out and makes contact. This wire comes out and makes contacts. So there are brushes that touch that and make contact with them. Well, as this coil spins, when it spins, the magnetic field causes current to flow. Let's just call this A and B here. At this point, as it's moving, A is moving from north to south, isn't it? Let's say that moving from north to south provides a positive current. If we looked at this from above, Here's our coil from above, right? This is point A right here. Is point A moving? I should draw in some magnetic fields for you. Let me do those first. So here's my magnetic field from north to south. In fact, let me start with the coil like this. Now I'm going to put point A right here. If this is rotating in this direction, is point A currently going through many field lines? Is it crossing many field lines right now as it goes through here? Yeah, just point A. No, it's not. So that means very little current. So we're going to call that position 1. At position 1, point A is not crossing any field lines. As we keep moving, right here, that's point A. Now is it crossing field lines? Yes. Is it crossing quickly or slowly? Slowly. So as it goes up, that might be point 2 there. I drew that wrong. Point 1 should be up here. It's crossing them slowly, so it's a very low slope there. As we continue, now when point A is right here, position 3, is it crossing them quickly or slowly? A little more quickly, isn't it? Kind of in between right there. So it's accelerating. That's point 3. When it gets to right here, is it crossing them quickly or slowly? That's the quickest, and it's actually going completely perpendicular to them, isn't it? It's crossing the most field lines the fastest at that point. It's going to have the highest slope, point 4. How about here? Is it speeding up, crossing them faster or slower than it was before? They're slowing down. Does that make sense? It's crossing the field lines fastest when it's moving perpendicular. Let me draw my field lines out. So let's say, some more field lines in here. Let's describe our velocity as just a distance that goes in a certain unit of time, right? So here, if it moves that distance, it crosses a lot of field lines, so it's going exactly perpendicular. If it's going at an angle, in that same distance, it crosses fewer field lines because it's going, it's the same distance between them, but going at an angle, it has to go further to get to the next field line. Does that make sense? The shortest distance between points is a straight line. So if you're going perpendicular to them, you're going to cross them fast. Think of it as crossing the road. If you wanted to cross the road as fast as possible, you'd run perpendicular to it. No. Running at an angle like this, you're going to get across the road slower. If you're going like this, you're not going to get across the road at all, are you? So when we're here, that means that's 0 change in current in that wire. 0 influence. So that would be point 1 up here or down here at the trough of that wave. These points here, the equilibrium points, are right here where it's moving the fastest. That's when it's changing the most. That's the steepest slope on that curve. So that's how the AC power is generated, is like that. So every rotation of that generator is a cycle. So the generators, how fast do the generators turn, do you think? How many times do you think a generator turns in a second? How many cycles per second does the power coming out of your outlet have? It's how many hertz? 60 hertz. So those generators turn 60 cycles a second. So when you're speeding up, why is the sine wave? Because that's its steepest angle. That's the most rapid change. Well, if it's crossing this direction, one direction is negative, the other direction is positive. Faster the current is changing. Yep. It's really kind of weird. It's fascinating how it works. You ever look at like a wind? You ever see the windmills? You ever watch them how they turn? They're all turning the same speed. Um, if you ever time one once, video one and time it, if the wind is blowing lightly or if it's blowing strongly, they still turn at the same speed. They have restrictors on them. They turn, if there's not enough wind to turn at that speed, they don't generate power. But if it's as long as there's enough wind to turn them, if they are turning, they will turn at that speed every time. They are restricted so they don't go any faster than that because that is the speed. They obviously don't turn at 60 cycles per second, obviously. They're geared down inside there so that they're turning, the generator that they're turning turns at 60 cycles per second. They're the turbine hooked to a gear system for the generators. But that's why. I mean, even if the wind is just whipping, you look at that windmill and it is still turning the same speed. It doesn't speed up because it has to generate power at that frequency. So you can see there is a direct relationship between frequency and radial velocity for the power. The frequency is 60 hertz, 60 per second. What would the angular velocity be then for power coming out of an outlet? Yeah, 2 pi 60 or 120 pi radians per second. So when you are looking at the equation for that, since it is a sine wave, our voltage is our peak voltage times sine of omega t, where t is the time from the beginning of the wave, beginning of the cycle. If it's 110 volt power, what is our peak voltage? Yeah, it's certainly 120, what they use. It's 170 volts. I should have said 120 volt power. Times the sine of omega is 2 times pi times 60, or 120 pi, times t. So let's say you know you started a timer at the beginning of the cycle. What is the voltage? 8 milliseconds into a cycle. Well, that is 170 times sine, 2 times pi times 60 times 0.008. Now, before I punch this in, what do I need to make sure I do? Have to be in radians, yes. And I'm going to actually use the pi key here. .31 volts is where it would be at 8 milliseconds. When is the first time it'll be at 120 volts? Well, 120 goes in for the instantaneous voltage. That's equal to 170 times the sine, 2 pi times 60 times t. We're solving for t now. What's our first step? Solve this for t. Just like with our exponentials, we have to get the trig function by itself. So we're going to divide by 170. So on my calculator at 120 divided by 170. 0.7059, we're going to call it. Notice I am not clearing my calculator. I'm keeping that in my calculator so I don't have the round-offs. So I can keep just using the next or the answer function on my calculator. What's my next step? Inverse sine. So that's why I kept this in the calculator. I do inverse sine, second sine, second answer. 0.7837 equals 2 times pi times 60 times t. Well, now what I'm going to do is I'm going to divide by 120 pi. 2 times pi times 60. So I'm going to divide by 120, then I'm going to divide by pi. 0.00208. What that is saying is that it's 2.08 milliseconds after the start of the cycle. Will be the first time it reaches 120 volts. What do you guys think? How about the current? Our instantaneous current is equal to our peak current times the sine of omega t. In other words, our instantaneous current is equal to the peak current times the sine 2 pi ft. Of course, frequency is 60. Up above, the peak voltage was given to us. How would we find the peak current? Peak voltage divided by, what's Z stand for? Have you guys talked about impedance at all? Way back when? Impedance in an AC circuit is the equivalence to resistance. So it's basically your resistance. Resistors have resistance, wires have resistance, capacitors and inductors have impedance. It's what the force that they press back against the current with. So let's say we have 170 volt peak current, and let's give you a 40 ohm impedance. It gives you 4.25 amps is your peak current. This 40 ohms has to be given in order to be able to do that. So if you're wondering where the 40 ohms came from, I just pulled it out of my head. So find the current 3 milliseconds into a cycle when the voltage peak is 170 volts and the impedance is 20 ohms. Let me guys try that one. I'll give you a second or two. So it doesn't matter if you find the peak current first or if you just put it in the formula like I did here. It'll be 170 divided by 20. That part's going to happen first times the sine of 2 times pi times 60 times 0.003. My parentheses. 7.69 amps. Pretty close to the peak because your peak current there is going to be like 8.5 if you figured that out. So that's pretty close to a peak. Any questions? Okay, in your packet. Page 371, 372, 1 through 53. Have a look at the odds. Obviously, you don't have to do all of those because there is a lot of them. Do some of the easier ones, skip ahead. Make sure you can do some of each variety.